Was your exam there? Oh, okay. I did grade it, and you did well, but it could just be sitting up on my desk, so. See if I can get this volume halfway right. Okay. Well, thanks for coming. Sorry for a little bit for the late start. I'm actually recording this, hopefully. So if others who can't be here want to hear the wonderful questions that you ask in the material that we go through. Oh, sorry. Still have tape on my fingers. I just got done playing tennis, so. And now I won't be able to get the tape off. It happens all the time. I have some nerve issues in my fingers from years of tennis. It's exciting. And if I tape my fingers, it helps. All right. Okay. So one thing I want to point out before we do get started, don't forget to look under week 15 in Sapling. There's quite a bit of stuff there. There were some frantic students who emailed me yesterday and this morning saying they thought that 12 p.m. was midnight Saturday night that it was due, plus Blackboard was down for like at least 5 hours on Friday. So the homework is back open till 10 o'clock tonight. Okay? I didn't want it open today because you should be studying for your finals, but if you haven't finished it, it's still open. There is a study guide that's just a topical list of what you need to know from each chapter. Here's the equation sheet that you'll get with the exam, just so you know what's going to be on there. Don't print that. I mean, you can print it out if you want, but you don't need to bring that with you. That will be on the exam, with the exam. There'll be a periodic table as well. Here's the practice final. Here are just the answers. Here's a detailed answer key. If you want to listen to me talk through all the problems, you can do that as well. And then I did run more straightforward review sessions last year where I kind of just said from chapter 1, although we used a different book so the chapters might not quite line up, but I went through and said from chapter 1 you need to know these things and here's some example problems and whatnot. So since that was already recorded, you can go do those. I thought it would be better this year, since I have that already, that we could just talk about anything you have questions on that you're concerned about going into the final. So, somebody start us off. Okay.
The freezing and boiling point.
Freezing and boiling point. Okay. Yes, we did kind of just we rushed a few things at the end. I apologize for that. And again, I already mentioned this, but here's the equation sheet. The way it's laid out, there's a few conversions at the top. All the constants that you should need come next, like Avogadro's number, Planck's constant, the ideal gas constant, and so on. And then there are equations after that. Okay, so I went through the exam again this morning, tried to make sure that every equation that you need is on there. And then there's a solubility chart. Okay? Oh, and it's actually, I don't know why that printed on 2 pages, but it won't be like that for the exam. And then again, of course, there's a study guide as well, plus the practice final. All right, so let's just, let me get a blank sheet of paper here. Okay, so freezing point depression. Boiling point elevation. Okay, that's one thing you need to know. We didn't have enough time in class to explain why. I can give you a very quick explanation. The freezing point for a liquid to freeze, the liquid molecules have to get together in a more ordered arrangement. If you have a solute dissolved in that solvent, it's going to disrupt those liquid molecules coming together. Okay? So you're going to have to get the temperature of that solvent lower before those liquid molecules can order up. Okay? It's kind of opposite for the boiling point. For a substance to boil, it has to be at the surface of the liquid. Okay? And so if we're just boiling water and it's just pure water, all we have at the surface of the liquid is water. But if we dissolve sodium chloride or some other soluble substance in water, now there's going to be some of that substance at the surface. So in effect, the surface area of the solvent, maybe it's water, is you don't have as many molecules at the surface. So you're going to have to get that to a higher temperature to get the solvent into the gas phase. Okay? So that's why when you dissolve a solute in a solvent, it's always going to lower the freezing point. It's always going to raise the boiling point. Okay? Once you know that, it's actually pretty easy to calculate the change in the freezing point or the change in the boiling point. The change in the freezing point, you just need a constant that is dependent on the solvent. And you need, you need molality. Okay, and we talked about what molality was in class on the last day. Molality, I'm sorry. I've got two mics going, and plus there's the mic on the computer itself, and if I get too close, they all want to talk to each other somehow. So I have to try to stand back from my computer a little bit. All right. Molality, mole solute. Kilogram solvent. So most likely on the final exam, some problem, you're going to have to calculate molality. Okay, it's not too bad. You should be familiar with calculating moles, and you should be able to convert from, say, grams to kilograms or whatever you need to do. Okay, so once you have that, this constant would be given. Okay, it is solvent dependent, but it would be given on the exam, and you just multiply those two together. If you happen to get a boiling point problem, it's the same thing. The change in the boiling point is a boiling point constant. It will be different for that particular solvent. The freezing point constant you don't expect to be the same as the boiling point constant, but it's also multiplied by the molality. Okay. The other thing to keep in mind, one more thing and then I'll answer your question. The thing to keep in mind, this is just the change in the boiling point or the change in the freezing point. Okay? So you're going to have to, for the freezing point depression, you're going to have to subtract that from the normal freezing point. If it's not water, yes. If it is water, you should know for water that the normal freezing point is 0 Celsius and the normal boiling point is 100 Celsius. Okay, if it's a different solvent, it would be given. Okay, but you should know the normal freezing point and the normal boiling point of water. Question?
So in Amber's study session for these, we talked about there being like an I equals 2.
Yeah, that's not on the final. So you can, if you have something like sodium chloride, so when sodium chloride dissolves, it actually breaks apart into Na plus and Cl minus. So the number of particles in solution is double the sodium chloride concentration. So for every one NaCl, you get one Na and one Cl minus, one Na plus and one Cl minus. So your concentration is in effect double. So that I she was talking about for sodium chloride would be a 2. So you would in effect put a 2 in front of that. We're not going to do that on the final. Okay, but that's just counting. It's just depending on the number of particles you have in solution. And salts, when they break up, you're typically going to get more, for every one salt, and they're not molecules, but one salt formula unit, you're going to get 2 particles, 3, 4, depending on what the salt is. Okay, but for the final, this is sufficient. Yes?
So for the freezing point, we subtract, but for the boiling point, is the second step where we add?
Well, so the boiling point, it's boiling point elevation. So when you get that change in the boiling point, you're going to add it to the normal boiling point. Okay? So for water, say that we got a say we just got a change in freezing point of -3 Celsius. Okay? Well, The new freezing point for water, you're going to subtract that from 0. Okay, so the new if this were water, so if this was for H2O, you're going to subtract that, so the new freezing point for water is going to be 0 minus 3, so it's going to be a negative 3. Well, sorry, let me back up. These are always going to come out to be positive because the constant is positive and molality is positive. So you're not going to get a negative number here for the delta. So you're going to have to know that's going to come out to be positive. You're going to have to subtract that from the normal freezing point because it's going to lower the freezing point. And so it'd be negative 3. For the boiling point, you're going to add whatever delta you get to 100 if it's water. Okay, freezing point depression, boiling point elevation. Is everybody okay with that? There is a practice problem. There is a problem on the practice final. We did one in class. It's pretty straightforward. As long as you can calculate molality, you just take that, multiply it by the constant that's given, but realize that's the change. And you're going to have to deal with subtracting from the freezing point or adding to the boiling point once you get that delta. Is that sufficient? Yes. Sure. Let me open it. I don't have it open on here. Practice final. That's not the right one. Oh, I probably just copied the same one from last year. Enough exams there for you? Trying to find the practice final. Here's the answer key. All right, this will work. All right, 67. Is that right? Okay. Okay, so there's a couple of good things in this question on the practice final. One is to understand how boiling point or melting point would change with the strength of the intermolecular attraction. Okay, so the first thing that's kind of contained in this problem so the stronger the intermolecular attraction, the higher the boiling point. Okay, so that's a good thing to know going into the final. Okay, if the liquid molecules are more strongly attracted to each other, you're going to have to put more energy in to get that substance to boil. Okay, to break those attractive forces. Okay, so that's one thing to know going in the final. So this right away is telling you the boiling point of I2 is higher than F2. So right away it's telling you that the attractive forces in iodine are stronger. Okay, so that's a good thing to know. But then it's also then asking what type of intermolecular force or intermolecular attraction would that molecule have. Okay, and that's where you have to go to a couple of things, but mostly to polarity. Okay, so you have to know, is that a nonpolar compound? Is that a polar compound? Is it a special type of polar compound that has an OH bond or an NH bond or an FH bond? Or potentially, is it ionic? Okay, because ionic are different. Okay, so that's kind of what you need to look at. Nonpolar, polar. There's a special type of polar called hydrogen bonding. And then there's ionic compounds. Okay? So, iodine or fluorine, we have the two of the same atoms bonded to each other. So are those polar or nonpolar? Don't make this hard. These are nonpolar. Okay, they're going to share the electrons the same. Okay, so since they're the same types of atoms, they're going to share the electrons equally, and both of these are nonpolar. So what type of attractive forces exist in nonpolar compounds? Dispersion force, or also called London dispersion force. Okay. Now those exist in all molecules, but in nonpolar, that's all you have. You only have dispersion force attractions. Okay. So the correct answer for this, what type of intermolecular force? It's a dispersion force. Now, the last point in this problem to make sure you're aware of going into the final, why does I2 have stronger dispersion force attractions than F2? Okay, so I2 does have stronger attractive forces. These are dispersion forces. Higher boiling point. Why? Dun, dun, dun. What's that?
Larger in mass.
It's larger in mass. Okay, so the larger the, technically it's not just mass, there's other factors that can come in, but for our purposes, the larger the molecule, the more electrons there are, the more easily the molecule can form these temporary dipoles. And that's what a dispersion force is. It's just a dipole that forms at some instant in time that attracts to another molecule. Okay, so for our purposes, look at molar mass. That'll, for the more often than not, that will get you the right answer. It'll certainly get you the right answer for the final. But the larger the molecule, the easier it can distort and form these instantaneous dipoles, this dispersion force. Okay? So I2 is a larger molecule. So it's a good thing to start with. Freezing point, boiling point. We got a little polarity and attractive force. Let's go here and then we'll go over to you. Yes?
Can you do 39 on the test?
39. Okay, I like this problem. You'll see something like this on the final. So, do the projectors seem dimmer than normal to you, or is that just my eyes? Maybe it's just me. I don't know. It looks dimmer, doesn't it? Oh, well. The semester's almost over, so I guess that's a good thing. Maybe we should get the bulbs replaced before next semester. All right, I like this problem. There's a couple of good things in this problem. One is, do you know the difference between absorption and emission? And then the other is, do you know how energy depends on wavelength? Or we could change this problem. This one does have wavelength, but we could change this problem and make it about frequency as well. Okay. What happened? That just like came, and it rolled down the ramp and went right by me and I didn't even notice. How observant. Somebody's rolling me a Skittle or something, I don't know. Okay, or an M&M. Okay, so those are the two things. Do you know the difference between absorption and emission? And then do you know how energy depends on wavelength in this case? Or we could reword the problem and make it frequency. Okay. So first thing, this one says absorption. So which of those are absorptions? A, B, and C. Okay, so promoting the electron from a lower energy level, or as Bohr called it, a shell in the atom, or an orbit, promoting from a lower energy level to a higher, we're going to have to put energy in. Okay, that electron is going to have to absorb energy to go up to a higher energy level in the atom. Okay, so absorption are A, B, and C. D and E would be emissions. When the electron drops from a higher energy level to a lower, it's going to release energy. It's going to emit energy. And some of that energy is going to be in the form of electromagnetic radiation. And if it's in the visible region, we will see it. Okay? There are plenty of transitions. Some are UV, some are infrared. We won't see those, but you get the idea. All right. So, A, B, and C are absorptions. Now we want the absorption of a photon that has the longest wavelength. Okay, so then you have to ask yourself, are you looking for the largest energy transition, or are you looking for the smallest energy transition? Longest wavelength, largest energy, or smallest energy of those three? Largest or smallest? I hear smallest, I heard a couple largest. How is energy and wavelength proportional to each other? One thing we can look at, and this will be on the equation sheet, you could look at that equation. Make sure you know that equation. We have wavelength, so that lambda symbol, that Greek symbol lambda, that's wavelength. So longer wavelength, larger number, plugged into the denominator here, what is that going to do to your energy? Smaller energy. So the longer the wavelength, the smaller the energy. They are inversely proportional. Okay, energy and wavelength are inversely proportional. So energy is proportional to 1 over lambda. Inversely proportional. The other way, if you want to think about it, we could draw out a couple of waves, and these are going to be awful, but you get the idea. Okay? So there's my wavelength here for that wave. Here's my wavelength there, much shorter wavelength for that top wave. Okay? And what determines the energy of electromagnetic radiation is how many oscillations of that wave you have per second, the frequency. If you have more oscillations per second, higher energy. If you have fewer oscillations per second, that's a lower energy. And so just by looking at these two, this is the lower energy wave, the bottom one. Okay? Longer wavelength, fewer oscillations per second, lower energy. Okay? The top one, more oscillations of the wave per second, higher energy. Okay, so it's not based on speed. All forms of electromagnetic radiation travel at the speed of light. Okay? And so it's not based on speed, it's based on the number of oscillations of that wave per second. Okay? So the other thing to know, but that's wavelength, so longer wavelength, smaller energy. And so we're looking for the smallest energy, which would be which one? A, 2 to 3. Okay. Now, we've already talked about frequency, counting the number of oscillations per second, but if we change this to frequency, energy and frequency are directly proportional. So if you had one with frequency, higher energy. Okay? Higher frequency is more oscillations of the wave per second. That's higher energy. Lower frequency is fewer oscillations of the wave per second. That's lower energy. So those are directly proportional. Okay? So there's a lot of good stuff going on in this problem, as you can see. A lot of things you should know. One more thing that you should know, and we didn't spend too much time on this. We did mention it, but make sure you realize that the energy levels get closer together as you go higher in energy. So this would be increasing E this way. They get closer together. So transition from 3 to 4 is smaller energy than a transition from 1 to 2. Even though it's just a delta of 1, 1 to 2 is a larger energy than 2 to 3, which is a larger energy than 3 to 4, and so on. So the energy levels get closer and closer together as we go further from the nucleus. Okay? All right. Good with that? All right. Question? Okay. So let me see where my blank sheet of paper went. All right. All right. So polarity, students quite often struggle with polarity. It's a fairly difficult concept in the sense that you have to differentiate, one, polar bonds from polar molecule. Okay, that's one thing. And the other thing is that the symmetry of the molecule and the shapes that we've done for quite a while, you kind of have to visualize those and see how things interact. So there's a lot of stuff going on with polarity. But a couple of key things to think about. If the molecule has high symmetry and it has all the same bonds, and I'll show you an example in just a minute, what can we say about the polarity of that molecule? It is nonpolar. Okay, and we'll do an example in just a second. Okay, what do we mean by high symmetry? Linear? Trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay, so those are the 5 basic shapes you need to know for the electron geometries anyway. Those are all high symmetry structures if all the bonds are the same. Okay? And there's one more that's not one of the 5 electron geometries that you need to know. It comes from octahedral. When you have 2 lone pairs, you end up with a square planar structure. And that's high symmetry as well. Okay? So that's one of the examples where you can have lone pairs and end up with a nonpolar molecule. Okay? So as an example, if you had something like this, okay, and I haven't put all the lone pairs on there, but there would be lone pairs around each of the fluorines. Okay? God, these screens are dim. What's going on? Feels like I'm fading here. I don't know. God, it seems like it's getting dimmer as we go on. Is it? Yeah. God, that's weird. Figures. They're gonna die on us as we're trying to get ready for the final. All right. 1, 2, 3, 4, 5, 6. 6 Vesper domains. So what's the electron geometry? Octahedral. Since there are no lone pairs, the molecular geometry is also octahedral, the shape of the molecule. High symmetry. All the bonds are the same. They're all SF, S to F, S to F, every single one. Boom, you're done. Nonpolar. Okay? Now, if you want to understand why that is, we can go further, and let's just do that for this example. This is certainly a polar bond. Okay? Fluorine is the most electronegative element. Okay, so make sure you know that, and then the trend, it would have to increase over to fluorine and decrease going down. Ignore the noble gases, they don't react. At least in nature, they don't react, so they don't have an electronegativity. Okay? So fluorine's the most electronegative. That means that these electrons in this bond are going to spend a little more time near fluorine. Fluorine builds up a partial negative. Sulfur builds up a partial positive. That is a dipole. That is a polar bond. Okay? So the typical way we show that is by drawing a vector showing the magnitude and the direction of that shift. Okay? So the electrons in this bond shift toward fluorine. Well, same thing on the other side of the molecule. All right? So this bond dipole is going to cancel with that bond dipole. This bond dipole is going to cancel with that one. Sorry. Got to be careful where I stand. All right? And again, it's because of the high symmetry of the molecule, those bond dipoles cancel out. This one pointing up is going to cancel with the one pointing down. Okay? So all of those bond dipoles, in effect, cancel out. We don't have one end of the molecule that's positive and one end that's negative. Essentially, this whole molecule is going to look negative on the outside because all the electrons have shifted toward the fluorines. So that molecule will not orient with another molecule because there's not a positive region on the outside and a negative region somewhere else on the outside. Yes?
The trigonal planar one.
Well, that one's a little harder to see. So that's why I always say, just have in your mind, if it's one of these high symmetry molecules, and trigonal planar is high symmetry, and if all three of the bonds are the same in the trigonal planar, it's going to be nonpolar. Okay? Now, how they cancel, if we have something like, okay, and this is not the correct Lewis structure of this, there'd be a double bond. We would draw 3 resonance structures, but this ends up being trigonal planar. So these are certainly polar bonds. Oxygen is more electronegative than sulfur. Oxygen is the second most electronegative element to fluorine. All right. Now, what is not easy to see, or particularly easy to see, particularly as these screens get dimmer and dimmer, is if we were to add this vector, this dipole, with this one. They are both pointing down, but this one's pointing down to your left, and this one's pointing down to your right. And if we were to add those two together, so a vector has a magnitude, so how big it is, and then a direction. Okay? So if we were to add those two together, what is called the resultant dipole would be that. So this bond dipole added to this one, if we add those two, we get this one one in green. And that one happens to be equal and opposite to the one pointing up. So they do cancel out. Yes?
I have a question. Is the structure going to be nonpolar for all and the bonds are polar?
Well, so pretty much anytime you have different types of atoms bonded together, it's going to be a polar bond. Okay? Sometimes the electronegativity difference between the bonded atoms is really small to the point that we'd say, oh, it's essentially a nonpolar bond. Okay? But for our purposes going into this final, if you see, in this case, sulfur bonded to oxygen, they're not going to share electrons. Just assume they don't share electrons equally, and they don't. Okay? So many molecules, you will have polar bonds, but have a nonpolar molecule. Okay?
Since the sulfur and fluorine one all had like an equal amount of bonds, is that why that one didn't get like an extra one added in the middle to cancel out another?
Which one are you looking at?
The sulfur chlorine.
Uh-huh.
You know how on sulfur and oxygen how
Oh,
those two bonds created one, but because that one's they all have like an equal amount.
yeah. Yeah, so the octahedron, just the way that the molecule is, the way the bonds are arranged, this dipole is on the opposite side of the molecule, so, the ones in the square plane are opposite to each other. That's easy to see. And the one pointing up and the one pointing down are opposite to each other. That's easy to see, right? So that one, the symmetry of the molecule is a little easier to see that the dipoles cancel. The trigonal plane is a little bit harder. The tetrahedron is a little bit harder to see that the high symmetry of the molecule, that these bond dipoles do cancel out. But they do. Okay, trust me. Or trust yourself. All right? And then just keep this in mind. You need to know these structures anyway for the final. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar. If you have one of those high symmetry structures and all the bonds in the molecule are the same, it's going to be nonpolar. Now, if we change one of these bonds, and so in this SO3, if one of these is not oxygen, then it's going to be polar. By changing one of the bonds, you've reduced the symmetry of the molecule. And if you reduce the symmetry of the molecule, most likely it's going to be polar. Okay? Now, the other thing to think about, the other big thing to think about in terms of polarity, is if you have a lone pair or pairs of electrons on the central atom, generally that reduces the symmetry of the molecule. And if you reduce the symmetry of the molecule, it's usually polar. Okay? So let's write that down. Okay? So anytime you reduce the symmetry of the molecule, typically the molecule is polar. And lone pair or pairs on the central atom typically do that. Now, there are some exceptions to that. Okay? And the one kind of exception that we've already highlighted up here is this square planar structure. Okay? So this is kind of the common example that you will see. Xenon tetrafluoride. Okay, practice a little naming here while we're doing this. Okay, xenon, we don't have to say monoxenon. We don't say monoxenon because if it's the first element that we have in the compound name, if we say xenon, it's understood, but there's 4 fluorines tetrafluoride. 1, 2, 3, 4, 5, 6 octahedral. Electron geometry, but there's 2 lone pairs. Okay, so there's our octahedron electron geometry, 6. 2 are lone pairs, and we end up with the square planar structure, which is high symmetry. Okay, xenon tetrafluoride, these are certainly polar bonds. Fluorine is much more electronegative than xenon. So we have a polar bond, okay? And if you're watching this video, I'm pointing at a model, so you can't see this. But I have the square plane with 1 fluorine up and 1 fluorine down. Those are certainly going to cancel. And then 1 fluorine to your right and 1 to your left. And those would certainly cancel. Okay? So lone pairs don't always reduce to symmetry, but usually they do. So those are kind of the two big concepts or key things to think about when you're doing polarity. And that will get you through 90+% of the times. And it should get you through polarity on the final. Okay? Now, keep in mind, you could have a molecule like we started with back on the practice final, like I2. Okay? So don't be confused by molecules like that. Those are nonpolar. You don't even have to go, oh, is that linear or is that whatever? It's just two atoms bonded together. They're the same. They're going to share electrons equally. Nonpolar. Oops. Sorry. Versus something like that. That molecule would like to say hi to you. You're supposed to say hi back. Okay. It's Sunday night. What can I say? Okay. So since that's just two atoms bonded together, assume they're not going to share electrons equally. Okay. And then we would just say that's polar. Okay. So simple molecules like that, boom, you don't even have to think about. Okay. But a little bit more complex molecules, you have to look at the structure and see is it high symmetry or not. So for some of them, you're going to have to draw out the Lewis structure, see if there's a lone pair on the central atom. If there's a lone pair on the central atom, it's probably polar. Okay? Does that help? Yeah, make sure you go through the practice final and look at ones with polarity, because polarity you're going to see in a variety of different ways on the final potentially. It could be a question that's just which of these molecules, it's multiple choice, the final. So it could be which of these molecules is polar, or which of these molecules is nonpolar. But it could be a question with intermolecular attractions, and it could be which of these molecules has the highest boiling point. So if you're looking for the highest boiling point, you're looking for the one with the strongest intermolecular attractions. So certainly a polar molecule is going to have stronger attractions than a nonpolar molecule, and you need to be able to identify that. Okay? You also may see polarity in a concept that we did on the very last day, and again, I apologize for doing a lot of things on the last day. Like dissolves like. Okay? So like in terms of intermolecular forces. Something that's nonpolar is more soluble in a nonpolar solvent. Okay? Something that is polar is more soluble in a polar solvent. Okay? So there's a variety of different ways that you might see polarity on the final. So make sure you can look at a molecule and say, is it polar, is it nonpolar? Also watch out for hydrogen bonding. Does it have an OH bond in it? Does it have an FH bond in it? Does it have an NH bond? Molecules with those are just strong dipole-dipole attractions. They're polar, but it's a particularly strong one, so we call that hydrogen bonding. Wyatt. Do double and triple bonds affect the polarity? Yes, if it is a true double or triple bond, that it's not part of resonance. Okay? So, for example, when I drew SO3, that's not the complete Lewis structure for that. Okay? The Lewis structure, when you draw that out, you would actually put a double, it'd be a double and two singles to get the octet on sulfur. Now, if that really were two singles and a double, that molecule would be very slightly polar. Okay, because the bonds aren't the same. And the double bond is going to have more electron density than the single bond. So it's going to be a little bit different polarity-wise. Okay? So if you did have a molecule that had a double bond and two singles, yes, it would be slightly polar. But this molecule does not, because there's two more resonance structures where we move the double bond to the other two locations, and all the bonds end up being identical when we average those three resonance structures. Okay? So in this case, all three bonds are the same, nonpolar. Yes, Catherine?
So if it's on that list and it has all the same bonds, it's definitely nonpolar. Like,
Yes.
is there like 5 fluorines?
Well, if it's trigonal bipyramidal, so something like PF5, okay, so here, I'll give you 2 examples with 5 bonds. PF5, okay, versus and you might want to, in your, when you go back and you're studying a little bit later, draw those Lewis structures out and make sure you can draw those. But if you draw out PF5, you're going to get 5 bonds. Trigonal bipyramidal, 5 Vesper domains. Okay? So this would certainly be nonpolar.
Even though there's like not even number of bonds that kind of cancel each other?
Well, they do. So this one, the fluorine pointing up, the bond dipole cancels with the fluorine pointing down, and then you're left in the middle with the trigonal plane. And we talked how the trigonal plane cancels out separately. I mean, when we talked about SO3, right? But this bond dipole, if we want to go through the trigonal plane again, so the 2 bond dipoles in the trigonal plane pointing to the right, okay, if we were to add those 2 together, we would get a resultant that would point between those 2. And that resultant happens to be equal and opposite to the one pointing to the left. Okay, so those all do cancel out. Okay, but compare that to BRF5. So the first thing you see in this structure, if you draw this Lewis structure, is you're going to see a lone pair on the bromine. And right away, that should trigger and say, oh, lone pair, it's probably polar. Probably. Okay, and in this case, it is polar because the bond dipole pointing up doesn't have a bond dipole to cancel with the one pointing down. This happens to be a square pyramid. So if you take your octahedron, okay, so that's 6. So count your electron domains. 5 bonds, 1 lone pair, 6 domains. That's octahedral, but one of those is a lone pair. Okay, so we're left with, and again, somebody watches this video later, I'm holding a model of a square pyramid. This bond pointing up does not have a bond to cancel with it pointing down. So this will be a polar molecule. Yes? Well, so we didn't go past octahedron because now you're saying 6 with a lone pair. We didn't go to molecules with 7 pairs of electrons around the central atom. There are some of those that exist. There are some with 8. But we just did 2 through 6. Okay, so 5 bonds, 1 lone pair. That's a square pyramid. That will be polar. Okay, does that help?
Yeah. Also, will there ever be a time that like lone pairs will cancel each other out? Because I know bonds can cancel each other.
Well, yeah. So technically, a lone pair is a region of electron density. So this lone pair down here will partially cancel with this bond, but they're not going to be the same. They're not going to be equal, so they're not going to cancel out. Now, square planar, there technically is some electron density up here from the lone pair, but the one down at the bottom is opposite to it. So you don't typically you don't have to look at the lone pairs to figure out polarity. You typically do not have to, you look at the lone pairs to see if it reduces the symmetry of the molecule, but you don't have to look then, will a lone pair cancel with a bond? Well, you assume that it doesn't. You would assume that a bond dipole is not the same as, the electron density of the lone pair. They're not the same. Okay. Okay. Yes.
Can we go over number 28, please?
28. Can you guys still see what's up on the screen here? Let's see if it's... No, it's not. Let me just try something really quickly here. I'm just going to unplug this real quick and plug it back in. Oh, bonus. No, oh. Wow. I don't think it's my computer. I think it might be the HDMI connection. Or it could be my computer, it could be my HDMI, but it hasn't been like this before. Oh, that is so weird. Oh, I know what's going on. Hang on. God, sometimes it takes a while for your brain to clue in. I don't know how I can turn this off. So I have on my computer, it's probably a good idea if you guys, I think it's a good idea for anyone to do with a computer, is I do have on my computer that when it gets dark, it changes the screen to more of a reddish tint, which doesn't affect your sleep as much, because the computer screens tend to have a bluish cast, which tends to keep you awake if you're on the computer late at night. So it got dark and my computer screen went to red, and that's what we're seeing. And now it all makes sense. Now I have to figure out how to turn this off. So hang on. See if I can find it. It's just like automatic. Oh, buggers. So much for having, where is it? I thought it was on my desktop. Of course, I'm not going to be able to find it. Sorry, guys. Oh, well. All right, well, hopefully... That's weird. I wouldn't have thought that it would have made that big of an impact on projection, because it doesn't look that bad when I look at my screen, but it definitely does not project well. All right, at least now I figured out why. Maybe if we take a break in a little bit, I'll see if I can reboot and reset this. Okay. So again, I apologize it's still visible, but it's not great. So barium chloride is mixed. What? Oh, 28? I thought, gosh, see? All right, 28. I knew that. I was just testing you. Okay. All right, so we have a reaction. Okay. Looks like it's balanced, so that's a good thing. And then we start with 25 milliliters of 0.1 molar HCl. How many milliliters of 0.2 molar barium hydroxide would it take to react completely with the HCl? So it's talking about a reaction. It's talking about you have a certain amount of one reactant. How much of another reactant do you need? Your first thought should be, this is a stoichiometry problem. Okay? And anytime you go stoichiometry, your next thought should be, I have no idea. Oh, no, it doesn't like my... Sometimes when I have computer recording, it runs low on memory, so then it tells me that it can't do colors, but it's okay. So stoichiometry, once you identify, okay, you know something about one reactant, in this case it's asking about another reactant, stoichiometry, then your very next thought should be moles. Very next thought should be moles. Okay? The way we compare things in a reaction, moles of one thing to moles of something else. Okay? So those are our for stoichiometry, we're thinking moles. So the other thing that I would look at before we do that is we have 0.2 molar barium hydroxide. We want to solve for, well, let's write it this way. Molarity is moles per liter. Okay? So I do know the molarity. Eventually, this is what I want to solve for. I want to solve for the volume of that barium hydroxide solution. Okay? So the other thing I need, I have molarity. To be able to solve for volume, the other thing I need is moles of barium hydroxide. Okay, so that's another thing to think about as we're working this problem. Moles of barium hydroxide is not given. But if we can do some stoichiometry, we can get to moles of barium hydroxide. So again, once you identify stoichiometry, think moles, look at your HCl. The HCl, we have the molarity, and we have the volume. So what can we calculate? We can calculate moles. Molarity times liters gives you moles. Okay? So remember the molarity equation, molarity is moles per liter. If we cross multiply here, molarity times liters will give us moles. Okay, so don't forget that. So solution stoichiometry is a little bit trickier. But always keep in mind for solutions, molarity times liters will give you moles. Now, in this case, it's not moles of barium hydroxide, it's moles of HCl. But that's okay. We can do some stoichiometry and take care of that. So for the HCl, if I take the 0.1 molar, which is moles per liter, times, now you're going to have to convert that 25 milliliters to liters. So divide that by 1,000, and you're going to get 0.025 liters. The moles of HCl is going to be 0.0025 moles of HCl. So molarity times liters gives you moles. It's good to know. All right, now, we don't want moles of HCl. We need moles of barium hydroxide so that with the molarity and the moles, we can solve for volume. So how do I go from moles of HCl to moles of barium hydroxide? Mole ratio. So coefficient of 1 for barium hydroxide. Coefficient of 2 for HCl. So this will give me 0.00125 moles of barium hydroxide. Okay? So we're not quite done. So a couple of good things in here. This is a stoichiometry problem. Stoichiometry is about moles. If it's solution stoichiometry, quite often you're going to have to get moles taking molarity times liters. So we've done that. Molarity times liters gives us moles of HCl. We want moles of barium hydroxide. We apply the mole ratio from the balanced equation. Now, if we look back, what we have up there, we know the barium hydroxide is 0.2 molar. We now know how many moles we have of barium hydroxide. Let's call our liters X, and then we need to solve for X. Okay? So if we cross multiply here, 0.2 times X, 0.00125. So x must be 0.00625 liters. Remember, molarity is moles per liter. So that x that we solve for is in liters. What unit do we want for this problem? Milliliters. So there's 1,000 milliliters per liter. Okay, so we could write out a conversion. 0.00625 liters, 1,000 milliliters in 1 liter. And you're going to end up with 6.25 milliliters. Did I do that right? Does it match the answer on the answer key? I hope so. So solution stoichiometry is a little harder than the grams to moles stoichiometry. But always keep in mind, stoichiometry is about moles. That's one thing. And for solutions, don't forget, molarity times liters is how we get moles. Okay? Yes? All right. 40. All right, so electron configurations will certainly be on the exam. You will also have a periodic table on the exam. So make sure you know how to use your periodic table to do electron configurations. Okay. Now this one does not use shorthand notation. So, we're going to start in row 1 over here on the periodic table, and that's going to be the 1s, so that'd be 1s2. Then we come down to the second row, 2s, that can hold. So remember, the layout of the periodic table is really nice. It's laid out in this way based on properties, but, the S block is on the left, these two columns. The P block is on the right. The D block is in the middle. Okay, so S, P, D orbitals. F is down here at the bottom. Don't worry so much about the F orbitals. Okay. All right. So second row, 2s, that can hold 2 electrons. We come over to the P block. The P subshell can hold 1, 2, 3, 4, 5, 6 electrons. Okay. Third row, 3s, that can hold 2 electrons. The P block again, 1, 2, 3, 4, 5, 6, 3p6. Then we get down to the fourth row, 4s, that can hold 2 electrons. And then what orbitals fill here? The first row of the transition metals. 3d. So the D is one behind the S. So the S and the P go together. So fourth row would be 4s. And then if we did move all the way over to the right, 4p. But that middle row of the transition block, that first row of the transition metals is the 3d. So then we count across 6. 1, 2, 3, 4, 5, 6. And we end up at iron. Right? Oh, is it 4s2, 3d? Is that 5 or 6? I can't see. Is it? I can't. Oh, it is 3d5. So we end up at 1, 2, 3, 4. We end up at manganese. Okay, so sorry, the D and the number kind of blurred together. So this is 3d5, and so we end up at manganese. Is that okay?
I'm just the whole electron configuration thing still confuses me. So the first row would be S1, right?
So 1s, and that can hold 2 electrons. So anytime you have an s orbital, you just have one of those, and any orbital can only hold 2 electrons. Okay. Second row, 2s, that can hold 2 electrons. So electrons 3 and 4. So if you're looking at the numbers on the periodic table, that would be electrons 3 and 4. This is where the p orbitals fill. And anytime you have a p subshell, there are 3 p orbitals. There's the px, the py, and the pz. So each orbital can hold 2. for a total of 6. And if you count across, 1, 2, 3, 4, 5, 6. Okay? And then the third row would be 3s and 3p. The fourth row would be 4s, but then 3d. Okay, the d is one behind the s and the p. Okay? And the d orbitals, anytime you have a d subshell, there are going to be 5 of them. Okay, and that's why if you count across the transition metals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 electrons can be held in the 5 d orbitals in that subshell. Okay? So just find where you are. So 4s2, 1, 2, 3, 4, 5 in the 3d, that is manganese. Okay? All right, lots of good questions. Yes?
For 41, it's like asking things for the last, and I get that it's D, but I'm also confused why it's not S, because aren't you first filling the D subshell before you fill the S?
For transition metals, the S fills before the D. And I mean, all you have to do is look at the periodic table. So these first 2 columns of the periodic table, that's where the S block fills, and then the D comes after the S. Okay, so we're going to fill in order based on the periodic table. So for transition metals, the S fills before the D. Yes? Empirical formula. All right. So, it's been a long time since we've done an empirical formula calculation. But one thing to keep in mind is that the subscripts in a formula, one way that we can read them is in terms of a mole ratio. Okay, it can be an atom ratio as well, how many atoms in one molecule, but it can be how many moles in 1 mole of the compound. So in this type of problem where you're given mass percent data, you want to calculate an empirical formula, you should also be thinking moles, because we can read the subscripts in a formula in terms of moles. Okay? Now, this compound is 36.84% by mass nitrogen. The remainder is oxygen. So oxygen must be 63.16. Did I do that right? Okay. Now those are mass percentages. So we're going to have to start, it doesn't tell you what mass of compound you have. And even if it did, don't worry about that, because there's an easy amount of compound to assume. And what would be a good amount of compound to assume that we have in terms of mass? 100 grams. Okay. You don't have to, but even if the problem tells you have a certain mass of compound, I would just assume 100 grams, because that means we're going to have 36.84 grams of nitrogen in 100 grams. So assume 100 grams, 36.84 grams of nitrogen, 63.16 grams of oxygen. Okay. Again, as we talked about, we can read the subscripts in the formula as a mole ratio. So let's do that. Can convert to moles. 1 mole of nitrogen, 14.01 grams. Read that off the periodic table. 1 mole of oxygen, 16 grams. So for nitrogen, we get 2.6. How many sig figs do we have? 4. It's 2.6295. So that's about 2.630. And for oxygen, about 3.948. Okay. So that is, if you can see that, maybe you'll be able to sleep better tonight. You get the red computer screen. That is the correct mole ratio. So we could write a formula with the numbers, and that'd be the correct ratio of nitrogen to oxygen, but formulas we want to write with whole numbers. Okay? So if we write out, we get just a little bit more, oops, let's not do that. Oh, that was not smart. So if we write out a formula N 2.63 and oxygen 3.948, we would like to get to whole numbers. So what should we divide by? Divide by the smallest. Because if we divide by the smallest, we're guaranteed to get one whole number. We're going to get 1. Okay? So divide both of these by the smallest. And if we do that, we get N1 and about oxygen 1.5. So that's looking better. And we're closer to getting a formula with whole numbers. But we're not quite there, so what should we do? Multiply by 2. Okay? So don't round that 1.5. You can only round if it's really close. Okay? So if you were at like 1.97, yeah, round that to 2. But 1.5, certainly we wouldn't want to round that to 2, or certainly, not truncate it to 1. So sometimes you're going to have to multiply by a small factor. I think it's pretty obvious to see it's 2, but if you don't see it, start with 2, see if you get a whole number. If you don't, then go to 3, and so on. But if we multiply each of those by 2, we end up with N2O3. Okay? Is that okay? Well, you would need the molar mass of the whole thing. And you would compare the molar mass to the mass of the empirical formula. You would need the molar mass. You would divide that by the empirical mass, and it would show you the factor by which the molecular formula and the empirical formula are related. Okay? You might divide the molar mass by the empirical mass and get 1, which would tell you they're the same. But you might get a factor of 2 or 3 or 4 or 5 or whatever. It shows you what multiple the empirical, the molecular formula is. Okay? Yes? 23. All right. So calcium fluoride, the first thing we need to do is we need the correct formula of that. If we're going to decide what it's going to dissociate into, we need to figure out what we're looking at. Okay? So let's look at where calcium is in the periodic table and where fluorine is in the periodic table. So calcium is an alkaline earth metal. It's in group 2. Okay? So when it reacts to form an ionic compound, how many electrons is calcium going to lose? Okay? So when we form ionic compounds, remember the metal is going, so we're most of the semester we focused on what's called the main group elements, the first 2 columns, and then the P block of the table over on the right. And if we focus on those, the metals are going to lose electrons to reach a noble gas. The nonmetals are going to gain electrons to reach the noble gas electron configuration. Okay? So calcium, if it loses 2, it will end up with the configuration of an argon, electron configuration. So calcium is going to form a 2+ ion. Fluorine, which is a halogen, is only 1 away from the noble gases. So how many electrons would fluorine gain? Just 1. Okay? So it's going to be -1. Okay. Now, compounds are electrically neutral, so we need to write that formula in such a way so that our charges balance. So what do we need here to make the charge balance? We need 2 fluorides. Okay. So this reaction, when calcium loses 1 electron, that 1 electron is going to go to 1 fluorine to make fluoride. The second electron is going to go to a second fluorine to make a second fluoride, F minus. Okay? So the 2 electrons lost from calcium, one's going to go to 1 fluorine atom, the other's going to go to a second fluorine atom. All right, so you definitely need to know how to write correct formulas for ionic compounds for the exam, so that was good practice. Now we need to break this apart. So what we assume for soluble salts, soluble ionic solids, we assume they dissociate completely into ions. They're going to break apart into cation and anion. Okay? The calcium one is easy to see. There's just one of those. So we're going to get a calcium 2+ ion in solution. So that AQ means that that's hydrated by water. Okay? Now, the other ion is fluoride. How many fluorides are we going to get? Piece? Yes, we are going to get 2. Okay? So again, calcium losing 2 electrons, we need 2 fluorine atoms, each gaining 1. We're going to have 2 fluorides. So okay. So be careful. It's very common. Students quite often will think, oh, it's just going to be F2 minus. It's going to be these 2 things together. But this subscript of 2 tells us that we have 2 fluoride ions in solution. So that salt is actually going to, for every 1 formula unit of that salt, it's going to break apart into 3 ions. 1 calcium ion and 2 fluoride ions. Do you have a question?
No, I was going to say, so if you had 2 calcium and 4 fluoride, it's breaking 6 ions.
Right, yeah. So, but, yeah, I mean, we wouldn't have that particular situation because ionic compounds are always written with the simplest formula. So we wouldn't have Ca2F4 because that would be reduced to CaF2. But let's see if we can think of another example. If we had something like, I mean, this is not quite what you were getting at, but if we had titanium 4 chloride, okay, so I just named this titanium 4. If you look at the charge of chloride, chloride's going to be -1. So 4 times -1, titanium's going to be +4 to balance the -4 of chloride. So in terms of naming that compound, we'd call that titanium 4. So writing it out, it would have a Roman numeral 4, chloride. That particular salt, we'd get 1 titanium 4+ ion. And because of that subscript of 4, we would get 4 chloride ions. Now that doesn't have the 2-to-4 ratio because we wouldn't have that because it'd be simpler, but yeah. That didn't help, did it?
It's just confusing. It's not confusing, but another thing is, like, the charge is equal to ions. Is that always going to happen?
No.
Okay.
Let me give you another example where that is not the case. Let's do... Well, this one's not soluble, but let me just do... yeah, so let's do this. This would not be particularly soluble, but in terms of just assigning charges. Oxide, being 2 away from the noble gas, is going to gain 2 and be 2-. So then what is titanium? 4 plus. So the charges do not, I mean, this one, happens to match that, but that doesn't, see what I'm saying? So, but sometimes it does. Yeah, I mean, sometimes, with 4 plus and minus 1, they end up matching, but. What do you mean the coefficient? Sorry.
There's one calcium and 2 fluorides, so that's 3. There's one titanium from 4 to fluorides, so that's 5.
In terms of the number of ions in solution?
Yeah.
Well, yeah, I mean, so if we were counting, how many ions would we have in solution for every one formula unit? Yes, it would be 5. Yes, Catherine?
Can you go over number 17?
If I can find it, there it is. All right. So you're given a balanced equation, and it says how many molecules of oxygen are produced when you react 0.82 moles of potassium chlorate, or when 0.82 moles decompose. All right. So we have the amount of one thing in the reaction. We want the amount of something else. Okay, so your first thought is what? Stoichiometry. And if you're thinking stoichiometry, you're also thinking moles. Now, this one gives you moles of potassium chlorate, which is nice. It's already starting you out with moles. Okay? But I want to know something about oxygen. I want to know about molecules of oxygen. So I want to get to oxygen. How do I do that?
So you would do 2 moles of potassium chloride, and then compare that to how many moles of oxygen.
Okay. So you have a coefficient of 2 for potassium chlorate, coefficient of 3 for oxygen. Okay, so there's your mole ratio. So since the problem started you with moles, we can just apply the mole ratio straight away. 3 moles of O2 for every 2 moles potassium chlorate. Again, arrange it so that moles, in this case the potassium chlorate, cancel. We would now have moles of O2. All right, and you could do a calculation here and actually get the moles if you want, and then do the next step, or we can keep going. We don't want moles of O2, we want molecules. How many molecules are in a mole? How many particles in a mole?
6.022 times 10.
Avogadro's number, 6.022 times 10 to the 23rd. So we want moles to cancel. We want to end up with molecules. 1 mole, 6.022 times 10 to the 23rd molecules or particles. So since it's O2, we don't call that an atom. It's 2 oxygens together. That's called a molecule. So that many molecules per 1 mole. Again, we arrange it so that our units work out. Moles cancel. We are now left with molecules of O2. And I guess we can finish. Let's go ahead and get an answer here. .4, we only have 2 sig figs times 10 to the 23rd molecules of O2. Okay? Yes? Okay. Give me just 1 sec. I just thought of something. See if I go to... Oh, that was interesting. Doesn't show that's weird. Figured that the program that I have that's running, making the screen red, would show up, but it's not. Oh, there it is. Let's see if that did anything. Now the screen's completely blank. Oh, now nobody's going to be able to sleep tonight. Whew. Let there be light. God, how come it took me like an hour to figure out that I could just go into Task Manager and end that? Not very smart. Oh well. Okay, now we can see. All right, what was the where's the I'm sorry. What was the question? 34. All right. So we have a balanced equation. That's good to notice. And we're given a delta H with that equation. We're given the heat flow for that. So a couple of things you should know. Delta H, first thing you should notice, it's negative. So what does that tell you? Is that endothermic? Is it exothermic? Exo. So that's a good thing to know. So this is an exothermic reaction. That much heat is going to be released. The other good thing to know is that is the heat flow for that balanced equation. Okay? So as we look at that reaction, when 2 moles of carbon monoxide react with 1 mole of O2 to produce 2 moles of CO2, that is the amount of heat that's released, 566 kilojoules. So it's for that balanced equation. If we react a different amount, we're going to get a different amount of heat released. Okay? So this is 7 grams. It's probably not, sorry. We're having all sorts of computer fun tonight. That 7 grams is probably not 2 moles of carbon monoxide. Okay? How many moles is it? Can we find out? Okay. So if we calculate the molar mass of CO, carbon is about 12.01, oxygen is 16. We're going to get about 28.01 for the molar mass. Okay, 12.01 for carbon, 16 for oxygen. Okay, so that's 7 grams of CO. Is only about 1/4 of a mole. And to 3 sig figs, 0.250 moles CO. Okay, so that's certainly something you need to know for the final, how to convert grams to moles. Don't miss a problem like that. You would kick yourself later. So that's the heat, that 566 is the heat that's released when 2 moles reacts of CO. We only have 1/4 mole of CO, so right away we know it's going to be significantly less than 566. So that's a good thing to know. You're going to have a multiple choice final. If you have any answers that are larger than 566, if you had this problem, you know those can't be right. It has to be smaller. Okay? But how are we going to get the amount or the delta H for 7 grams? And this is where we actually kind of have to do a little stoichiometry with our heat flow. It's negative 566 kilojoules per 2 moles of CO. So we can write a conversion factor for that. Okay? We are only reacting 0.250 moles of CO. But we know we're going to get negative 566 kilojoules per 2 moles of CO. Does everybody see where that comes from? Okay, so 566 per 2 moles. All right. We are only reacting 0.25 moles. As you can see, our moles will cancel. We set it up that way. If you flipped it and put moles in the numerator, the moles wouldn't cancel out. We wouldn't get to kilojoules. And in this case, this is going to be about a negative 70.8 kilojoules. Okay? Which again, look at your answer. If it was 566 for 2 moles, we're only reacting an eighth as much. A quarter mole is only an eighth as much as 2 moles. So that looks to be about an eighth as much heat. If we had multiplied by that 8 by 8, we should get that 560. Okay? So that is kind of another stoichiometry problem, but related to how much heat is released. All right, so we're almost at 6:40. We still have time for a few more questions. We will meet again tomorrow, same time, same place, so 5 o'clock tomorrow. It'll be kind of your last chance to get some questions answered before the final. Make sure, I'm sure you know, but the final is Tuesday morning at 10, and we are not in this room. If you're in section 6, you're in the Weta building, the large lecture hall in the Weta building. If you're section 7, you're in the large lecture hall 106 in the Science Annex, which is just south of the Weta building. It's the old chem building, my old stomping grounds. Glad I don't have to stomp there anymore. All right, next question. 60. All right, how many sigma and pi bonds are there in this molecule? Let's do that first. So a single bond. What kind of bond is a single bond? A sigma. Double bond. 1 sigma, 1 pi. Triple bond, this doesn't have triple bonds, but a triple bond is a sigma and 2 pi. All right, so all we have to do is count every bond. 1, 2, 3, 4, 5. It's pretty easy. 5 sigma. And then the double bond is going to have 1 pi. Okay? So single bond is a sigma bond. Double bond, sigma pi. Triple bond, sigma 2 pi. Okay? Next thing, what types of orbitals overlap to form this sigma bond? Okay. So hybrid orbitals is something to keep in mind. Hybrid orbitals can only sigma bond. So if it's asking what types of orbitals are forming the sigma bond, they are going to be hybrid orbitals. Okay? So this is where you have to go to your VSEPR. So for carbon, each carbon we're going to count the same. We're going to count 1, 2, 3 electron domains. We count the double bond just as 1 electron domain. 1, 2, 3 electron domains. So the electron geometry is what? For 3 electron domains? Trigonal planar. Okay, so make sure you know that. 2 electron domains linear, 3 electron domains trigonal planar, 4 electron domains tetrahedral, 5 electron domains trigonal bipyramidal, 6 electron domains octahedral. Okay, so this is trigonal planar, 3 electron domains. And then what hybrid orbitals have a trigonal planar arrangement? sp2. That S did not write very well. Let's try that again. sp2. Okay, so the hybrid orbitals, sp is where we start. Sp hybrids are linear. They're going to match the basic shapes. Sp linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, sp3d2 octahedral. Okay, so those hybrid orbitals shapes will mirror the 5 basic geometries. Okay, and then, so that answers the what types of orbitals overlap to form the carbon-carbon sigma bond. Hybrid orbitals can only sigma bond. They cannot pi bond. If you have an orbital that has any S character in it, it can only sigma bond. And so sp2, there's S character in that orbital, can only sigma bond. Pi bonds, for our purposes, are always formed from the side-to-side overlap. That's what a pi bond is. Sigma bond is direct end-to-end overlap of orbitals, like we'd expect. Pi bond is side-to-side overlap of orbitals, and for our purposes, it will always be p orbitals that overlap side-to-side. So p orbitals, if we think about their shape, p orbitals kind of have a peanut-shaped, or, I don't know how best to describe that. So these would be 2 different p orbitals. Okay, this is where in the middle, that's where the nucleus of the atom would be. Okay, and so these orbitals overlap in 2 different regions. They're going to overlap above the plane of the molecule, and they're going to overlap below the plane of the molecule. So those electron densities overlap above and below, and you actually get 2 regions of electron density for a pi bond. Okay, but this would be a pi bond, and typically they're formed from p orbitals. Turns out d orbitals can also form pi bonds, but we're not going to look at any examples of that. So pi bonds are formed from the side-to-side overlap of p orbitals. Hybrid orbitals are going to form the sigma bonds. Okay, and the other thing to point out, sp2, that's only 2 of the p orbitals, say the px and the py. Remember, in a subshell, a p subshell, there are 3 of them, px, py, pz. So sp2 hybrids are only 2 of the p orbitals. The 3rd p orbital can overlap to form this pi bond. Yes? 47. So again, one thing to point out, there are recordings that I have done in the past for this practice final, and so those are in Sapling. So you can go, if there's any questions we don't get done tonight or tomorrow, you can go and you can fast forward through those videos and find these problems already recorded. All right, 47. Which is largest in size? Okay. Now, if we look at I would look at a periodic table and find sulfur and find calcium. These are actually ions. And what do you notice about the similarities between these 2 ions? Argon. They both have the electron configuration of argon. Okay? So if sulfur gains 2 electrons, sulfide, it would have the electron configuration of argon. If calcium loses 2 electrons, calcium 2+, it's going to end up with the electron configuration of argon. So these ions are what we call isoelectronic. Same number of electrons, same electron configuration. Okay? So that's why we can compare these directly, because they are quite similar in the sense that they both have 18 electrons, the same electron configuration as argon. Okay? What's the difference between those 2? Because they're certainly not the same thing. What's different about them? Protons. Okay? So calcium, look at your periodic table. Calcium's going to have 20 protons. So calcium 2+ has 20 protons, attracting those 18 electrons. 18, yes, I can write. Sulfide only has 16 protons, attracting 18 electrons. Okay? So we certainly have different nuclei, different nuclear charges attracting the same number of electrons. Okay? Whichever nucleus has the stronger attractions for those electrons, the attraction is stronger, the electrons are going to be pulled in closer. And it would be smaller. If the attraction is weaker, the electrons can spread out further and the ion will be larger. So we're looking for the largest, so we're looking for the weakest attraction between the nucleus and those 18 electrons. Which one's going to have the weaker attraction? Are you sure? You just seem to be guessing. So essentially we're just looking at nuclear charge, right? This has 16 positive protons. Calcium 2 plus has 20 positive protons. So calcium 2 plus has a greater nuclear charge. It has a larger positive charge in the nucleus attracting those 18 electrons. Okay, that's going to be a stronger attractive force. More nuclear charge is going to pull the electrons in closer. Okay? Fewer protons, smaller nuclear charge, it's not going to have a strong and attractive force on those electrons. So this is going to be a weaker attractive force, smaller nuclear charge, 16 protons, attracting those 18 electrons. Sulfide will be larger. Okay, so smaller nuclear charge, weaker attraction between the nucleus and those 18 electrons. Sulfide will be larger. Okay, calcium 2 plus will be smaller. Okay? Yes, Catherine?
Just as like a general question about the final.
Uh-huh.
Have students in the past run out of time? Should I be sensitive
So-
to time management?
So I would say that most students, and I would probably put it in the 90% of students, okay, so in a class of, 180 students, I would say 90% will be done early. Okay, so the final's 50 questions, multiple choice. If you think about the exams that you've taken this semester, there are 24 questions, so almost half the final, and you get 50 minutes. So if you double that, that gets you to an hour and 40 for about what the final is. So most students on this final are typically done early. Now, there will always be, in a large class, there will always be 20 students or so that will be there till the end of eternity if we let you stay. And I'm just joking, but there would be students who would stay for 3 hours if we let them, or 4 hours if we let them. Okay, but I don't think most students will be pressed for time on this final. Okay, most. There will be some, but I don't think the final is too long. There will be students who will be done in an hour. Okay, there will be students getting up in an hour and turning the exam in. Some of them will be very good students, and some of them might not be. Might be a little bit weaker and just, have had enough. But it's certainly doable in an hour, I would think, for some students, to give you a feel for time. All right, we still have 9 minutes. Yes?
Okay, so I have a question that's on the recitation handout.
Okay, recitation handout's fine.
I understand how we get to the morality of this, but I don't understand why we use water.
Okay, so is this a freezing point one?
Yeah.
Can I see the problem?
Yeah.
Okay, So it says 200 grams of sucrose is dissolved in 800 grams of water. Okay, what do you know about sucrose? Huh?
Nothing.
Nothing. It's in almost everything we eat.
She said it's a carbohydrate.
It's a sugar. What kind of sugar is it? Huh?
I'm not sure on that one.
It is ordinary table sugar. Okay? I shouldn't say it's probably in everything. Most stuff has corn syrup in it, which is not sucrose, but okay. So it's a solid. And we're dissolving that in water. Okay, so what do you think your solvent is? If you're dissolving a solid in water, which of those two components do you think is the solvent?
Isn't it the sucrose?
No.
The water?
So there's the solute and the solvent.
Oh, it's water.
Water is your solvent. Okay, so for our solutions, this doesn't have to be the case, but really all the solutions we've looked at, the solvent is a liquid, and the solute is something else, usually a solid. Okay, so for molality, so since this problem, and let me just get another sheet here. What am I looking at? There we go. All right. So since this was 200 grams of sucrose and 800 grams of water, when we go to calculate molality, it's going to be moles of solute, which is the sucrose, over kilograms solvent, which is going to be the water. Okay, so that 800 grams is going to be 0.8 kilograms of solvent. And then you're going to have to use the molar mass to convert to moles of sucrose. So this question is, for those of you who haven't seen this recitation handout, it's asking to calculate the freezing point of this solution.
But if we're doing it with solution, why are we just using water? I guess that's my question.
Well, so dissolving a solute in a solvent is going to lower the freezing point of that solvent. Okay, so compared to pure water, that's our solvent, we know the normal freezing point is 0 Celsius. Dissolving sucrose in there is going to lower the freezing point.
Okay, that answers the question.
Okay, so we want to know what is the new freezing point. Okay, and to do that calculation, we need to first get the molality. Okay, and then Kf is the freezing point constant for water, which would be given. It's 1.86 degrees C per molal, and we multiply by the molarity. Okay? And I think if we want to, do we want to finish this problem since we have it up here? Okay. So the molar mass of sucrose, correct me if I'm wrong, is about 342.3 grams per mole. Is that right? The molar mass of sucrose? What do you have on your hand?
42.30.
Okay, 342.3. Okay, so we're going to use that to convert to moles. So let's do that here. 200 grams of sucrose. So sucrose, sorry, I should write the formula because a lot of you don't have this in front of you. Okay. Sucrose, C12H22O11. So if you add all that up, which you might want to double check because you'll probably have a problem on the final to calculate molar mass at some point. Add that up, you should get about 342.3. So 200 grams of sucrose, 1 mole of sucrose, 342.3 grams. So this is about 0.5843 moles of sucrose. Sorry. God, it's just weird. I have to, if I stand just in the wrong place. 0.5843 moles of sucrose. That is our solute. Our solvent was water. 800 grams, 0.8 kilograms. So molality, by definition, moles solute over kilogram solvent. And our molality ends up being, and I was not very organized in solving this, 0.7304 or so. Okay, so let's stop there. Not stop, but let's stop and just pause. Is everybody okay with calculating molality? Because that's actually the biggest part of the, probably the biggest calculation part of this is just getting the molality. We had to convert grams to moles. We had to convert grams to kilograms. We had to divide those. Okay. Now that we have the molality, getting the change in the freezing point is actually quite easy because we just take this constant, which is given, times the molality that we just calculated. And the change in our freezing point is 1.36 degrees Celsius. Okay, so that's how much the freezing point compared to the pure solvent will change. All right? And then this is where you have to then know, well, what's going to happen to the freezing point? Is it going to be lower or is it going to be higher than the pure solvent? And which one is it? It's going to be lower. So dissolving a solute in a solvent will always lower the freezing point and raise the boiling point. Freezing point depression, boiling point elevation. Okay? So it's going to lower the freezing point of water by 1.36. And this is where you do need to know the normal freezing point of water. And that is what? 0 degrees Celsius is the normal freezing point of water. It's going to lower it by 1.36 degrees. So our new freezing point, that freezing point of the solution, is going to be negative 1.36 degrees Celsius. Okay? All right, I think we'll call it there for tonight. Apologize for my computer that I had that color correction on. I'd never even thought about that. Don't teach at night that often. But if you don't have one of those on your devices, it's actually a good thing. There's some free ones out there. This one's called Iris something, Iris Mini or something, and it's free. And it just automatically sets to the clock on your computer. So at night or early in the morning, if you get up like at 5 and start working on the computer, it'll still be red. And then as it gets brighter, it goes more to blue. And it automatically adjusts. So probably a good thing to do. So your exam would have been white. So if it's in there, it's in that stack.